I believe you can use them for all of those. I don't see a problem. The only thing I think you have to keep in mind is whatever the group. I'm going to write this because if I just say it, it might be confusing. So we can't use it for carboxylic acids because remember that hydrogen is going to be too acidic. So that won't work. If we have amides, though, we would have to have like a completely substituted amide. So something like this could work. If that's protonated, though, and there's a hydrogen attached to it, that hydrogen would be too acidic for it to work. Same goes for thioesters. So we don't want to have a hydrogen. These will work. If those are protonated, they wouldn't. Acyl chlorides, yes. Acid anhydrides, or acetic anhydrides, yeah, I believe that would be fine. You're welcome. Okay, so let's say he gave you this, and, or actually I'll give you an exam-like question. So let's say he gives you give me like 2 seconds to write it. We get A. Okay. So let's say he gives you something like this, right? It looks like a confusing multi-step problem if you just kind of look at the multiple arrows, but we know we have our bromine here, we have magnesium, so what are we going to end up making for A? Yes, so we are going to make the Grignard's reagent. So we get this guy. So this is product A, or intermediate A, I should say. And then from here, we're going to react that with our lactone. Why do I do that every single time? So the Grignard reagent, which I'm just going to redraw here for simplicity, as our carbons with the negative charge. So that's going to come in and attack, and I'm just going to go ahead and like do this all in one step. So I'm going to draw all the arrows at once. So we hit that, we bring those electrons up, we're going to bring those electrons back down, and we're going to kick off the leaving group. I know it's a lot of arrows at once, but since we did it a couple times, it might make sense. If you want me to draw it out, I can. But so all this means is that we have to open up our chain. 1, 2, 3, 4, 5. I just like to start at the carbonyl. That's 1. That's 5. So attached to the carbonyl, we have our new carbon chain that was added. We know that it's 3 carbons attached from the middle. And we know that on number 5, we have an O minus. So at this point, what are we going to do? Ooh, awesome. Yes, we can react again. What other little problem do we have to take care of? Awesome. Protonate. So you can either do this at once or in two different steps, however you want to do it. I just like to do it as two different steps. So I like to react again first. Attack. Bam. Kick up those electrons. So now we have O minus up here with our two new carbon groups added. And then we are now going to protonate with H2O. And we're just going to go ahead and protonate twice. So that steals a hydrogen. And this steals a hydrogen. And we end up with this guy. And I'm going to move it over just a little bit because it looks kind of ugly. Ta-da! And then someone asked, do we always react twice? So we are going to react as many times as we can when we reform the carbonyl. So if at any point you reform a carbonyl, you will react again. If you don't reform the carbonyl, you're not going to react again. Another way you can say that is if you have a leaving group, you're going to react more than once. That sort of kind of makes sense? Kind of. So just think about it as we're always going to react at least one time, and then every leaving group adds a +1. So in our lactone here, we have one leaving group. So 1 + 1 gives us 2. So we're going to react twice. If we had 0 leaving groups, it would only react one time. If for some reason we had 2 leaving groups, it could react 2 times. Plus the original 1. I can draw it out if you want me to, if it still doesn't make sense. But I will also zoom out so you can see that. He might also give you something very, very similar to this, but instead, the first step will be something like this. He likes ones like this, because it puts chapter 12, or even 11, so chapters 11, 12, and 17 all together. So you guys know PBr3 is going to do what? Turns OH into Br. Awesome. If it was PCl3 or PCl whatever, it would be a chlorine. And then at this point, we know we're going to make the Grignard reagent. So that will be B. And then we react with the lactone to get the answer, which would, in this case, be the same here. So it's pretty much the same exact thing. He's just adding this additional step to make sure you still understand what protecting groups do. And PBr3 specifically, because we use that all the time. Cool? Do you guys want to go into the chapter 17 practice problems now? You're very welcome. Yes, okay. So I am just gonna stop sharing real quick so I can clear the handout or the practice problems. Sorry, give me like 2 seconds. All right, here we go. Sweet. Alrighty, so let's start sharing again. And so I know, oh, there's stuff in the chat. I didn't see that. All right, so the first question was about acid and base catalysts. So it just says, could we say that no matter what is reacting in the chapter, we can always have an acid or base catalyst? Are you talking about specifically chapter 17 or like a rule for... Okay, so for chapter 17, pretty much yes. For all the reactions, acid and base are going to work equally as well. The only thing you have to keep in mind is saponification. So I believe it's fine in acid or base, but it's preferable in acid. But that's only this one specific reaction. Since we're using OH, it just prefers H3O+. So yes, we use base in a way because we're using NaOH, but in order to protonate at the end, you want to have either H2O or some acid. But don't think of NaOH as a base. That is going to be our nucleophile in this case, because that's what's doing the attacking. You're welcome. Okay, so there's not two... Oh, and then I think there was another question. Oh, are we finishing chapter 17 in SI today? Yeah, so all we have left for chapter 17 is practice problems. So I'm going to go through as many as I can today, and then hopefully we'll get through all of it so we can start 18 on Monday. Alrighty, so there's not too many really good chapter 17 practice problems. And I feel bad going over the same ones over and over again. So I'm going to go over the spicy set of practice problems that I have that you guys don't have access to. And I'm going to pick out some good ones so that I have those next week in SI and tutoring. So you guys can get some better questions in there because I feel bad doing the same ones over and over again. And then... could we go over one of the questions from the SI handout? Yes, we definitely can. Let's just go over 2 or 3 questions from here, and then we'll go back into the handout. Sound good for everyone? Cool. So, I think there's another naming one. Maybe not. Okay, so we start with ethyl. Is what we start with going to be on the oxygen side or the carbonyl side? Oxygen, perfect. So we are looking for an ethyl. That's not an ethyl, that's gross. That's not an ethyl, that's gross. Definitely not an ethyl, that's gross. All right, so we kicked all of those out immediately. So now we have 2 carbons and 3 carbons. Remind me what an ethyl is. 2 carbons, perfect. So we know that this has to be our answer, but let's just double check the other side. We have 3-methyl butanoate. 1, 2, 3, 4. 3-methyl, and that's a butane. So awesome, we are totally right. And what am I talking about? D is our correct answer. Any questions? We good? Awesome. Could you scroll, please? All right, I know we didn't do this one last time. Don't look at the answer. All right, so we are rating these in order from most to least acidic. So I want you guys to take a second and just like look at these and like kind of figure out what functional group each thing is. And then I'm going to ask you guys to tell me just by the condensed formula what each one of these is. And yeah, there are a lot more Chapter 18 questions than there are Chapter 17. I don't know why he does that. I just think it's because a lot of Chapter 17 is more of the same. Sorry, give me 1 second. Sorry, that was my dad. Okay, so these are pretty straightforward. They're not too ugly, but what functional group is this guy? Carboxylic acid, awesome, and we're going to just say Ca. We know that this is water. What about this one? Yep, that's just ethanol. What's this guy? A triple bond, so it's going to be an alkyne. And NH3, is that an amine or an amide? Amine, super. Alrighty. So out of these options, which one of these do we know has to be the most acidic? Carboxylic acid, awesome. One, because acid is in its name. But what else makes that hydrogen super acidic? Inductive effects, the carbonyl, awesome. Yes, resonance, all that kind of stuff. So we can automatically kick out all the ones where carboxylic acid is not the most acidic. So we're down to 2. Now, which one of these do we know is going to be the least acidic? Oh, but real quick before we do that, someone said resonance question mark. So yeah, the biggest reason that they tell you in Orgo 2 carboxylic acid is super acidic is because of the resonance stabilization that we get of our carbonyl. But that kind of goes with inductive effects as well. All right, so you guys said that the amine is going to be the least acidic. So why is that? Why do you guys think amines are not very acidic? They're less electronegative. Yes, that's true. They act as really good what's? Bases. Yes, that's true. So amines are really good at being bases, especially if they still have their lone pair. So we know that the carboxylic acid is going to be the most acidic, and amine will be the least acidic. So between A and C, which one's going to win? A. Awesome. So any questions on this one? Okay, cool. I don't know why I didn't just download the one without the answers, but whatever. All right, so I'm pretty sure we did this one last time as well, but tell me the order of most to least reactive, and let's not even look at these answer choices. When we're looking at our reactivity chart that we did earlier, what was the most reactive? Yes, acyl chlorides or acid chloride. You can call them either. So the acid halide is going to be the most reactive. And then what was our least reactive one of all? The amide. Awesome. We know that carboxylic acids and esters are pretty much the same. And we know that sulfur is slightly less reactive than those. So which one of these answer choices shows that trend? D, exactly. So you are both correct. That would be our answer. You guys are killing it so far. So the sulfur is going to be more reactive. I don't know if I said that backwards, but it's going to be the acid halide, I'll double check that for you, but I do believe it's more reactive than esters and carboxylic acids. You're very welcome. Okay, so let's do this one. So we're going to break open the lactone, and before we do that, let me know what kind of lactone this is, please. Oh, we already did this. Do you guys not want to do it over again? Because I know it's a pretty straightforward one. Okay, cool. Just remind me what the answer is, please. B. Yep. Cool. I believe we did this one as well. And yes, it was a gamma lactone. So yeah, I believe we did all of those. This is where chapter 18 starts. So do you guys want to go on to the handout now? Because I know Andrew had a question about the handout. 92. My packet doesn't have a 92. On the 4th page? I don't understand why. Like, there's no rhyme or reason for these numbering. Oh, don't worry about nitriles. Dr. West said he's not going to test you on those. Because students, I was going to give you guys like a brief thing on nitriles, but he said he wasn't going to cover it, so I was like, there's no point in giving it to you guys. Cool? So, let's go back here. All right, do you want me to clear the page and we can go through some, or did you have a specific question? The one with the ester. This one? All right, so basically, this guy is going to be the leaving group. This one will be the nucleophile. And so if we do it like the short way, we can also do it the long way if you want. But essentially, we end up kicking off this hydrogen and kicking off the leaving group, excuse me. And we add the oxygen here, and we end up making an anhydride. Okay, so we got 2 good questions. One was, I thought the anhydride was more reactive. It is, so this is one of those questions where if we did it this way, we would get a more reactive compound, which is not favorable, but it is possible. So that's the reason I included one like this. There's like 1 or 2 like that. And so conceptually, you just have to know that it is possible, but it's not favorable. We don't want to go backwards in reactivity, but if we really, really, really wanted to make that happen, we could catalyze the reaction and make it go the other way. And then What happens if there's excess ROH? So do you mean like an alcohol, or did you mean like?
Here, I'll just explain it. Like, if you
Okay.
go to the top of the page, there was like a question on the homework where, yeah, like the first one, it was excess MEOH, and like it formed like
Oh, okay.
uh
That's a great question. All right. So, what I think it's asking for is once we get to this point and we have excess of this, does it want you to attack one more time and create like um, an acetal looking thing?
yeah.
Okay. So that I haven't seen him ask a question like that on the final, but it's kind of like a chapter 16 question. So if we get this guy and we have an excess amount of our alcohol, we can go in and react again. And at that point, if we kick this guy off, there would be no point in the reaction because we would get the same exact thing. So instead, we end up kicking this guy out. And so in the first step, okay, wait. In the first step, before we attack anything, we have an acid catalyst, so you guys know we're going to protonate that. Right? I forgot to mention that, and then I felt really bad. So at that point, we can add our O with an R group and our hydrogen. We know we want to kick this guy off, so what can we do to make it a better leaving group? Sorry about my screen. So what can we do to make this guy a better leaving group?
You can protonate it.
Yes, but there's like a special word for this kind of protonation. Do you remember what it is? Intramolecular. Awesome. So this oxygen steals the hydrogen, gives those electrons back. And I know this is going to get kind of messy because I didn't give myself enough room. So if you guys get confused, let me know. I'll redraw it. Alrighty. So then we can go ahead and bring these electrons down, kick that guy off, and you end up with something like so. Is that what they wanted?
Like I don't know if maybe it wasn't this question, but like there were two oxygens on the side with ethyls and then the carbonyl in the middle.
Okay. So if you can go back and find that question and send it to me, I'll take a look at it. Just because while I think this technically can happen, I don't think you guys ever do this in Orgo 2. So I'd be very shocked if that was it. But I know the homework is super weird. So if you can find that and send it to me, I will definitely look at it for you. Cool?
Okay.
Okay.
Like if we don't need to know it, should I just like not worry about it?
Yeah, that's what I would say. But like if it comes up again and you happen to see it, like just send it to me just so I can take a look and definitively tell you like you don't need to worry about it. Um but I've never seen that kind of thing before where he asked for like excess alcohol in this kind of reaction.
Okay.
So let me delete that. Alrighty. Any other ones of these that you guys want to cover? Because we still have a couple more minutes.
Could we do a really hard one? Like The one that you think would be the hardest out of all these?
Ooh, sure. Okay. So, oh, okay. So I like the ones on this page because these are like the harder looking ones. So let's do, let's do this one. People always get scared by this one. So, first of all, what kind of functional group is this guy? Anhydride, cool, so it's going to be a cyclic anhydride. And so we know that if we have our nucleophile here, we're going to attack one of these and we're going to break open the ring, right? So the hardest part for students tends to be figuring out what's going to break, where is it going to break, and like what's going to count as a leaving group. So you guys know that what kind of bonds do we use as leaving groups in orgo? Like, do we ever use carbon-carbon bonds? No carbon-carbon bonds. What about carbon to hydrogen? No, cool. What about carbon to a heteroatom? Yeah, sometimes if it's protonated, yeah, if it's a good leaving group, definitely. So we can either use this bond or this bond as a leaving group. None of the other ones would work. So just for the sake of like keeping everything the same, I always like to use the carbonyl on this side, but you could use either one and get the same answer. So the bond in red is the one that we are going to break. So this whole thing is going to be our leaving group. Let me delete that arrow and draw my electrons. So we're going to go ahead and attack here. We're going to break open the ring. And let's just count 1, 2, 3, 4, 5. We're going to have a 5 carbon chain. I'm going to zoom out a little bit. So 1, 2, 3, 4, 5. We know that on carbon 5, we have our second carbonyl, and we have an O minus here. And so let's look back at this guy. Since we attacked, we added an S with 2 carbons. And we know that this oxygen will eventually get protonated to give us a carboxylic acid. So I did that in the short way. We can also do it like the long way to show you guys how this actually happens. But what do you guys think of this one so far? Yes, we can do it the longer way for sure. I know ones like these are tricky looking. And then knowing which one would be the leaving group. So it doesn't matter. We could have either used this as the leaving group or we could have used this as the leaving group. So let me redraw this on a clean page and we can talk through it and like do the whole reaction. So we have this guy, and we know that either this bond or this bond can be the leaving groups, because for our leaving groups, we're only going to use bonds from a carbon to a heteroatom. We're never going to break carbon-carbon bonds or carbon-hydrogen bonds. So we know that these are the only ones that could possibly be a leaving group. We also know that this is a symmetrical ring. So it's exactly the same on either side. So we're going to get the same product if we use this as a leaving group and we attack here, or if we use this as a leaving group and attack here. You'd get the same ones. And then we react this with these reagents. And someone asked, sulfur couldn't be the leaving group, right? So if sulfur were to act as a leaving group, it would go backwards. So the reaction would go backwards instead of going forwards. So we wouldn't want it to be the leaving group for that reason. So I'm going to go ahead and choose this bond to be the one that breaks, just because I like to always attack the carbonyl on the left. So I'm going to highlight the leaving group in red. So that's going to be our leaving group. So in the first step, if we have a or N-acid catalyst, what are we going to do to this carbonyl in the first step? Yes, I can repeat that, no worries. So if we have an acid catalyst in our reaction, what is the first step going to be? What do we do to the carbonyl? Protonate, yes. So, bam, bam. And reminder, Dr. West likes to call this the activation step. I forgot how to draw a cyclohexane for a second. All right, so now we have this plus charge. That makes it more electrophilic. So now our nucleophile, and I'm going to zoom back in. Our nucleophile, which is this thing, but more specifically, what atom is going to be the nucleophile? The sulfur, cool. So these electrons on the sulfur are going to come over here and attack that carbon, kick up the leaving group, or kick up the electrons, I'm so sorry. These electrons will attack the carbonyl carbon and kick up the electrons. So now we get this side stay the same, nothing happened. On this side we have an OH, and we have our sulfur group. So now we have a kind of tricky spot where we have to make a decision, because we have two oxygens that could both potentially be our leaving groups. So we have to choose between oxygen A and oxygen B. Which one is going to do an intramolecular proton transfer and steal this hydrogen? What do you guys think? Okay, so we kind of got a split. So let's try A first, and then we'll do B. So if this guy steals the hydrogen, we end up with OH plus here. And then our sulfur group has these extra electrons. It's going to bring those electrons down, kick off the leaving group, and we get that. Alternatively, if we did oxygen B stealing the hydrogen, These arrows are going to look kind of weird. I apologize. But so there's so much going on. I'm trying to draw everything correctly. So I'm sorry if it's taking a second. All right. So we have our sulfur, which is now neutral. We have this oxygen that now has a plus. And so excuse me, my hand keeps moving my screen. So the electrons from the oxygen now will come down and kick off the leaving group. So we get I'm sorry, I know I'm being quiet, but I'm just concentrating so hard on drawing this right. 1, 2, 3, 4, 5. Okay. So our oxygen reformed the double bond. It still has this plus charge here because we didn't deprotonate yet. We kicked open the ring. So essentially what we did is this was our leaving group and we kicked it off. And so now if we zoom out a little bit, we can see that we had named this part the leaving group and it has been kicked open and brought to the other side of the ring. And this yellow bond was broken. So now we have one side to deprotonate and one side to protonate. So what can we do to fix those charges? We could definitely bring in H2O, but we could also do an intramolecular proton transfer just to make it faster. Instead of doing it in 2 steps, we do it in 1. So we're going to steal that hydrogen, give those electrons back. And so we end up with this dude. And so I actually forgot to draw this double bond. I'm very sorry about that. So which answer are we happier with? The left. Yeah, I think so too. And the reason I would say practice, or I always say practice these reactions a couple times, is just so you guys can kind of make these mistakes, do it both ways, and kind of see, oh, yeah, it would be a really ugly answer if we did it this way. So that's why it makes sense, you know, to go this way, or to protonate something, or to not protonate something, all that jazz. And so remind me, what is this side called? What's this functional group? This right here. A thioester, cool. And then this side we know is a carboxylic acid. So this is the one that students find to be the most difficult one. As you guys can see, it was really ugly at some points and there was so much going on. Do you guys have any questions about it? Does it make a little bit more sense how we chose the leaving group in this case? You're very welcome. Yay, I'm glad it makes more sense now. Cool, cool, cool. Okay. So I can stay on for another minute or so if you guys have any more questions. But if not, have a wonderful, wonderful day. I'll probably see you in SI. And if I don't, have a wonderful weekend as well. Bye.